Hi everyone. So in this video, we're going to be talking about slope fields. So essentially what a slope field is a graphical representation of a set of slopes that are obtained from a differential equation. So if you plug in values for x and y into a differential equation, you'll get a specific slope within that entire rule for all of the different slopes, right, or rates of change. So recall a first order differential equation represents a set of slopes at given points. Even if you cannot separate variables and integrate, you can still use a differential equation to plot the slopes for a function. And also, we're going to learn how to actually sketch the solution, specific solution, to a differential equation that otherwise we may not have been able to solve with some of our traditional solving methods that were covered in lesson 10.1. Okay, so let's get started with the first example. So it says, find the slopes given by the differential equation dy dx equals x squared plus 1 over y minus 2. Okay, so what we're doing is we're finding the slope at the point 1 comma 0, which simple as this, all you're doing is subbing in 1 for x, 0 for y into our dy dx equation. Now be careful with notation here. The way we're going to write this is dy dx, and then this is the evaluated at bar, the point 1 comma 0. And that would equal, so it's x squared, so we're plugging in 1 for x, plus 1, divided by y, which is 0, minus 2. So 1 squared is 1, plus 1 is 2, divided by 0 minus 2 is negative 2, we get negative 1. So the slope represented by the differential equation x squared plus 1 all over y minus 2 at the point 1, 0 is negative 1. So think about the fact that it has a negative slope there, right? So it is decreasing. Okay, B, we are doing the same thing, plugging in negative 2 for x this time and 3 for y. So remember, notation-wise, we write that as dy dx evaluated at negative 2 comma 3, which equals negative 2 parentheses squared plus 1 over 3 minus 2. Negative 2 in parentheses squared is 4, plus 1 is 5, over 1 is just 5. So at the point negative 2, 3, the slope is actually a positive slope, 5, and it is a fairly steep slope, right? Especially compared to the slope at the point 1 comma 0. All right, go ahead and pause here and try C, D, and E. And then when you're done, go ahead and unpause and you can see the solution. All right, so hopefully you had enough time to do that. We're going to do dy dx this time, evaluated at negative 4, negative 4. We are going to plug in negative 4 for x, negative 4 squared, plus 1 divided by negative 4 for y as well, minus 2. Negative 4 squared is 16, plus 1 is 17, over negative 4 minus 2 is negative 6. So we get negative 17 sixths for that one. Okay, and here dy dx, we're now evaluating it at 2, negative 1. So we have parentheses 2 squared plus 1 over negative 1 minus 2. 2 squared is 4, plus 1, we get 5, all over negative 1 minus 2, we get negative 3. So we get negative 5/3 for that one. Okay, so the last one says, why can't you find the slopes when y equals 2? Well, the problem is our differential equation is x squared plus 1 all over y minus 2. And when you plug in 2 for y, you end up with a 0 in the denominator, and this is undefined. So you can't find the slopes because the denominator would be equal to 0. And therefore, the slope, or slopes, right, would be undefined. Okay, so now we're actually going to get into slope fields. So if you've never seen this kind of grid before, it just looks like a normal Cartesian coordinate XY axis, except there's little dots, right? And each of those dots are going to represent a spot where we're going to draw in a slope. So what I would like us to do, I think it's already scaled by ones, but I'm going to add a couple of points here just to make it a little bit easier for me and for you when you're watching me plot these, when we're plotting these slopes. Okay, so we're not plotting points anymore, we're actually plotting slopes. So the way this works is we're going to draw the slope field that represents y prime is equal to y minus x. So the way it works is you pick a coordinate point. So let's pick, for example, 1, 1, okay, which is right here. And when I plug in 1 for y and 1 for x in y prime is equal to y minus x, I get 1 minus 1, which is 0. So I end up with a slope of 0, which is just a horizontal line. And so that's exactly what I'm going to draw in. A little tick mark that represents my slope here is a horizontal line. Now, what ends up happening when you're drawing these is you're going to start realizing that there's a pattern. Well, anytime y is equal to x, you're going to get a slope of 0 for this one. So you can go ahead and fill in those tick marks as a little horizontal line anywhere where x and y are equal. Oh, now be careful. I just put that tick mark there on accident because, oh, actually, no, that one's fine. So 0 minus 0, we're still good. Just be careful. Some of these you end up with things that are undefined. This case, no, because it's just y minus x. Had to catch myself because occasionally when you plug in 0, you get a 0 in the denominator. Sometimes other numbers. We'll see an example of that later. Okay, so now we're going to do the same thing, but we can pick another point. So like, what about 1, 0, right? That's right here. So we're plugging in 1 for x and 0 for y. So you get 0 minus 1. You get a slope of -1. So you can kind of think about the fact that it would look something like this, right? It's a negative slope. Okay, and so it doesn't have to be perfect. It just kind of has to be fairly close. And obviously, if your slopes are steeper than another one, you should make it steeper, right? If it's negative, it should look like it's decreasing. If it's positive, it looks like it's increasing. But I'm not looking for things that are exact. Like this might be just maybe a little less steep. I don't know. Oops, something like that, right? But it is a slope of -1 there. And so what you do is you fill in the whole rest of the slope field. And it's a lot. So I'm going to just take a moment and fill in the rest of these slopes. We can maybe pick a couple more to do together. So if I instead did 0, 1, right? We get 1 minus 0, which is a slope of 1. And so you can just keep plugging more in if you feel the need to. See how that's increasing now instead of decreasing. Maybe it should be slightly steeper than that, something like that. Okay. Slope of 1. Okay. Something like that. So go ahead, take a moment, fill in these. I'm going to fill in mine. I'm probably going to speed it up so it's not super, super monotonous. But keep in mind, like as I'm going up the y-axis, like this is the point 0, 2. So my slope should be getting steeper, right? As I'm plugging in these values. Same with these ones along the x-axis, except they're going to be negative slopes. So this would be like 0 minus 2, which is a little steeper, 0 minus 3, which is a little steeper, but negative, right? So you can kind of use those patterns to help you fill that in. And then it would be 0 minus negative 1. So we get a slope of 1 again, right? A little bit steeper, right? Okay, so here's the point in the video where I'm going to go ahead and speed this up, and then we'll go from here. Okay. Okay. All right, now that I have my slope field, I'm going to go ahead and show you how to sketch the actual solution curve given an initial condition. So be careful here. If you ever have to draw in a solution curve, it needs to go from edge to edge on your graph, and I'll show you what I mean by that. So A says sketch the integral curve satisfying the initial conditions y of 0 is equal to 1. I'm going to do this in blue so you can see. You go ahead and put a dot at the point 0, 1, which is right here. And then you follow your slopes, essentially. They'll guide you to where you need to go. And actually, these slopes are all the same. They're slopes of 1. Let's see. And so your solution curve is actually the one in blue. Okay. Part B, we are sketching the solution curve satisfying the initial condition y of 1 is equal to -2. I'll do this one in green. So go ahead and put a dot at the point 1, -2, which is right here. And what you essentially want to do is you want to follow the curve. So notice this is all decreasing down kind of like this. And notice I'm going from edge to edge. I'm going all the way as far as I can go and follow these curves. Following these curves, looks like we kind of have a turning point. Now, if you don't actually hit one of these actual tick marks and you fall kind of in between like I did, you take kind of an average. So you're kind of just going with the flow like this. Okay, so your second solution curve is in green. And so that's the gist of these slope curves or slope fields and sketching in those specific solutions to the differential equation using those slope fields. All right, so on the next page, there's just a few more examples. I think I'm just gonna pick one more of these. Let me pick one that has maybe some undefined areas. So let's maybe do number 4 together. Numbers 3 and 5, if you're curious to see those solutions, they'll be on my website, mrsfitzmath.com, under the Calculus, AP Calculus BC tab. All right, so let's take a look at number 4. So for the differential equation, y prime is equal to y over x, we're going to go ahead and sketch in the slope field. So I'm going to go ahead and draw in those extra numbers. I just like to do this, especially for videos, so it's a little more clear where I'm going. Okay, so we have y prime is equal to y over x. Now, keep in mind, anywhere that x is 0, which is anywhere on your y-axis, is where the slope is actually going to be undefined. So be really careful about that. And it actually doesn't become too big of an issue. We just don't draw any tick marks until we end up with the parts B and C where we have to draw in solution curves. And I'll kind of show you how we handle that. Okay, so let's start drawing in the slope field, y divided by x. Now, whenever y and x are equal, right, you're going to get a slope of 1, right, except for 0, 0, it's undefined. So we can go ahead and quickly, I'll do that in kind of the same color I did before, and all these are just going to be 1. Notice I skipped going over 0, 0 because I know that that's undefined. Now, anytime they're opposites, but the same in absolute value, you're going to get -1, right? Like this point right here at -1, 1, well, 1 divided by -1 is -1. So you're going to get -1 slopes. And so it's going to kind of look like an X. So we can fill those out. Okay, anywhere along the x-axis, except for at 0, 0, be careful, is going to be 0, right? So we'll get like a horizontal lines going on, right? Because 0 divided by these numbers. And then we can keep going. So then just kind of pick a couple. So it's y over x, that's a slope of 1/2, but it's going to be positive. Keep in mind all your slopes in quadrants 1 and 3 are going to be positive, right? Positive divided by a positive is a positive. And so it looks like it's getting less steep as we go this way. And here's where I'll probably speed this section up so you don't have to keep watching me fill all this out. So let me finish up my tick marks. Oh, whoops, I went all the way into that one. Okay. Okay, now that I have my slope field down, I'm going to go ahead and draw in the curves that satisfy those initial conditions. So part B, we have the point 2, -3. So I'm going to put my dot right there. And then we're just going to follow those, basically those slope curves or field tick marks in order to get our curve, our solution curve. So it kind of looks like this. Now I'm noticing that it's, as I go this way, I run into something that's undefined. And so when you do that, you put an open dot, okay? So open dot, and then we stop. That's it, okay? And actually, let me make this a little nicer. Kind of bugging me. I didn't do the best job ever. Make sure it always goes through that point that was chosen, which was 2, -3. Okay, let's go ahead and do the one for part C. We're going to go ahead and sketch using the initial condition 3, 0, which is right here. And it looks like we actually just get a horizontal line going this way. And then be careful when you run into that undefined part, it's an open dot, and we stop. Okay, so there's our solution curve. And that's how you handle it when your differential equation has some areas where the slope is undefined. All right, so go ahead and remember, do numbers 3 and 5, check your work using my solutions on the website. And then let's take a look at the next section. Okay, so the next section is on Euler's method. And so Euler's method is a much more precise way to actually solve these differential equations or approximate their solutions. Okay. So it allows us to actually graph the solution to a differential equation using a lot of, it's a little tedious, and we're gonna basically step by step kind of crank out what the points should be using this method. Okay, so what I've laid out for you here is a table that you can use. I would recommend kind of memorizing the way that this table is organized and set up. So that way, when you're taking an assessment, you can set it up just like this. Okay, so it says use Euler's method to construct an approximate solution for the differential equation dy dx is equal to y. Start at the point 0, 1 and use step size delta x equals 0.1. Okay, here's how it works. So we are starting at the point 0, 1. So that's what I'm going to put in for my first x and y. Now we know that dy dx in this case is equal to y. So if I'm at the point 0, 1, dy dx would be equal to whatever y is, which is 1 in this case. Then you're going to find the change in y, which is your slope, times delta x. So the change in y for this, delta y, equals our slope, which we just calculated is 1. That's your dy dx at that point, right? Times delta x, which it gives you is 0.1. So delta y is 0.1. Okay, so the change in y you just calculated, you are going to use that to actually move to your next spot. And so I'll show you how to do that once we actually fill in this table and get some stuff plotted. Okay, so remember, the change in x is 0.1. Okay, so that means after we go to x equals 0, we go to x equals 0.1, right? Because we're changing by 0.1. You can even actually do the rest of the x's. Then we're going to go to 0.2, right? 0.3, right? Because this is our plus delta x, which is 0.1, okay, each time. Okay, well, how do you end up with the next point, the next y coordinate? Well, that's why we calculated the change in y. When we change an x by 0.1, we change an y by 0.1. So we're going to go ahead and add 0.1 to our previous y coordinate. So this would be 1.1. dy dx in this case, would be 1.1 since it equals whatever y is. And then we calculate our delta y, which in this case would just be our slope, which is 1.1, times delta x, which is 0.1, and then that equals 0.11. And we're going to do it again. Now we're going to add 0.11 to 1.1, which is 1.21. Our dy dx would be 1.21 because it just equals whatever y is. Delta y would then be 1.21 times 0.1, which equals 0.121. And then we're going to go back through, add 0.121 to 1.21, and then we end up with 1.331. This actually gives us an approximate value for y of 0.3, which is about 1.331. And now with this table, we can plot the x and y coordinates, so that way we can get the solution to this differential equation with a starting point of 0, 1. So we go to 0, 1 and start there. Then I plot 0.1, and actually they scaled this very nicely for you. 1.1, which is right here. 0.2 is 1.21, just a little bit above 1.2. And 0.3 is about 1.331. So a little under 1.4. And so your curve, your solution curve looks something like this. Okay. Now you could also use this to kind of work backwards. We're going to kind of just do what we've done with the table. This is as much as we know about the solution to the differential equation, but notice the actual points themselves are a lot more precise. And you could even solve this differential equation because this one is solvable, and see how close we really got with this. Okay, so go ahead, or actually let's take a look at number 2. So it says solve dy dx equals y algebraically. Fill in the table. Oh, it looks like we are comparing them. So let's go ahead and compare them. So dy dx is equal to y. We're going to solve it algebraically, and we're going to compare it with the approximate values we just found. So we want to separate our variables. So this would be 1 over y dy is equal to dx multiplying by dx, just like in my previous video. This is technically a 1 there as a placeholder. We integrate. The integral of 1 over y would be the natural log of the absolute value of y, which equals x plus c. We could do e to both sides. We end up with y is equal to e to the x plus c. Remember, you can think of this as e to the x times e to the c, which really is just a new constant, e to the c. I'll call it c1, e to the x. Now, we know that the initial point that we're given is 0, 1, so we can solve for c. So we'll plug in 1 for y and 0 for x. It looks like c1 is equal to 1. And so our differential equation solution, the actual specific one that we just tried to graph, is y equals e to the x. And so when we plug in these points, we have 0, 1, 0.1. If I plug that into a calculator, it's about 1.105. If I plug in e to the 0.2, that's 1.221. And e to the 0.3 is about 1.350. So if we compare that to our table, it's pretty darn close. 0.1, we got 1.1, right? 0.2, we got 1.21, very close. 0.3, we got 1.331, right? Pretty close to 1.350. Now, obviously, the closer you are to your starting point with Euler's method, the more accurate it actually is. So be careful with that. You really only want to go so far with Euler's method in doing this approximation. All right, let's take a look at the last page. Okay, so this one, you are going to do Euler's method to approximate the particular solution to the differential equation y prime is equal to x minus y, passing through the point 0, 0.5. Let delta x equal 0.2 and do 3 steps, n equals 3, and graph the points. So go ahead, you're going to start at 0, 0.5. Your dy dx, you just take your x coordinate and subtract away your y coordinate. So in this case, it would be negative 0.5. Your delta y is just your slope, which is negative 0.5 times delta x, which was given to us as 0.2. Wrote a little bit too big there. So we get negative 0.1 for our delta y. Okay, remember our delta x is 0.2, so my next point is going to be at 0.2, then at 0.4, then at 0.6, right? We're going by 0.2s. And then remember delta y was negative 0.1, so we're subtracting 0.1 from 0.5 to get a y value of 0.4. Okay, so 0.2 minus 0.4, we get negative 0.2, and then we have to calculate delta y, which is your slope, negative 0.2 times delta x, which is 0.2, and we get negative 0.04. All right, plugging in 0.4 for x, and we get, let's see, y, we're subtracting away 0.04, so we get 0.36, and then we do x minus y, so 0.4 minus 0.36 is 0.04. So delta y, we take our slope, 0.04, times our delta x, which is 0.2, and we get 0.008. Next one, to find that y coordinate, we're adding 0.008 to y. So we end up with 0.368, which tells us that y of 0.6 is approximately 0.368. Okay, so what we can do is start plotting those points, 0, 0.5, 0.2, 0.4, 0.4 is 0.36, 0.6 is about 0.368. Well, it's coming up a little more than that, maybe. And so it looks, oops, solution curve looks something like this. Okay, and that's really as accurate as we can get with it because we really only know those points that we've calculated. Okay. And then the very last one says sketch a particular solution to the differential equation y prime is equal to x minus y, passing through the point 0, 0.5 using the slope field given. Do the two graphs coincide? And so, yeah, so what we're going to do is we're going to go to 0, 0.5, right? And we can sketch in our slope curve. And do these look alike? They look pretty darn close. I mean, the tendency is where it's increasing and decreasing is about the same. May not be perfect because really number 4 is way more approximated than number 3 was. But you can see how these two methods are really similar, going to give you similar results, similar shaped graphs, but the method with Euler's method is just a little bit more precise. All right, that is it for today. Thank you.